Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're honored today to have Ayel Amir with us, visiting from the University of Illinois at Urbana-Champaign. Ayel is a professor there, and he's been there for several years. Before that, he did some postdoc work at UC Berkeley, and right before that, he did his PhD at Stanford University, working with John McCarthy, Sheila McElraith, and others. I came to know Ayel with some of his innovative work coming out of his PhD work and shortly thereafter linking logical reasoning with probabilistic methods and looking at issues of separability of axiomatic bases. I thought it was very, very interesting work. And he's gone on to do some I guess, more central UAI work after that later on. He's the winner of a number of awards, including the Arthur L. Samuel Award for Best Computer Science PhD Thesis at Stanford University. That award often is a century for great things to come. I've known some other winners of that award in the past that have gone on to do great things. Today, Ayel will be talking about two topics, one, reachability under uncertainty, and the other, Bayesian inverse reinforcement learning. So, Ayel.
Thank you, Eric. Thank you all for coming and actually being in this room. And also thanks to the virtual audience looking at this talk. I just want to give you a brief, kind of before I start with the talk, this is my group circa a couple of years ago. And so, as always, the work that you're going to see is really my students and only partially mine. So Alan Chang here is now he went to do to the startup world to make a lot of money, but he also is in this contributor half of this talk, and the other contributor is Deepak Ramachandran. Next year he's going to be on the market, so look forward to seeing him perhaps in person. All right, so I'll go now to the topic of this talk. So I'm going to talk about two separate topics. They come from trying to cast traditional problems in a slightly different view. One of them is the problem of reachability in graphs, and the other one is inverse reinforcement learning from the actions of experts. And I'm going to try, the two talks are slightly separate, but I'm going to try to tie them together towards the end. All right, so here's the first problem. It's something that we started working on about a year and a half ago. It's an interesting, very simple problem. You're trying to find reachability or shortest path in a graph. Have a source and a sink. This is in this case, the graph is directed. You can think about it as an undirected graph as well. And you're trying to find the shortest path, the path that minimizes the sum of costs along the edges of the graph. All right, so this is a very typical, well-known problem. There are very standard solutions for it. What we're looking at are generalizations of this problem. And here we're looking at cases where the edges may fail. So typically, if we have a probability for the edge to fail, then we can say that the path altogether is reliable if the product of the probabilities is high. Now, there is a hidden assumption there, and people have used that assumption over the years, and that is that the probabilities are independent. So the edges may fail independently, and we want to drop that assumption. By the way, the motivation for this was just a kind of discussion that I had with some of the security people in my department that were looking at finding those paths in the internet or any network where the probability of the path failing is the least. And so what we're going to do is we're going to try to make some dependence assumptions about those, and we're going to look at one particular example of a model, and we'll see what we can do about it. Okay, so I'm going to first present this notion of correlation that I'm going to use in this talk, and then I'll show why standard probabilistic techniques don't work. I'll show that actually the problem is an NP-hard problem, and I'll show an approximation algorithm for how to solve that. So here is a stochastic setting. So let's say that we have this very simple path, and we have random variables that represent the probability of those edges failing. Now let's assume this is we're going to create an extra node here, and that will kind of represent the correlation between those three random variables. So remember, each one of those variables is the probability that the edge will fail. Okay, so this is a very simple graphical model. To those of you who are familiar with machine learning, this is a very simple naive Bayes-like model. So when you look at the distribution of, or the distribution that governs the probability of the path being reliable, you notice that the path is reliable if the marginal here is high. So probability of edge 1 reliable, edge 2 reliable, edge 3 reliable. That is the probability. That's the marginal probability that the path is indeed reliable. Now notice that what we do to get to this marginal is really sum out this hidden variable x. This is the hidden variable that we represent. We use to represent that correlation. So the way that we get to that marginal is by summing out the variable x. So here's one application of this. The application that we started with is really that we notice that links may fail stochastically and routers will fail stochastically, and there is some correlation between the times that a link or a router will fail. If two routers have the same version of software on them, then they have some, they will be susceptible to the same viruses, to the same problems. Similarly, if you have, say, if certain lines were actually built with the same material and so forth, you can see that those lines will be correlated, and the fact that we don't know if those routers have the same kind of, what is this, let's say, if we are not sure of what is the virus that is going to attack this system, or we're not sure about some other elements, those will be those hidden variables that we're going to include in that model. Yeah.
So earlier you showed dependencies between edges over the same path,
Mm-hmm.
and now you're assuming dependency between any edge. Any
Right.
edges.
Right. So this, I'll flip back to that model. Here I showed it. I showed this. I'll show you the entire path. So I showed this on the path, but really it's a variable that controls all of the edges in the graph. It's just that I focused on a particular path. Okay, so this probabilistic model here, this is a representation of the joint probability that we will look at. So the probability that edge 1 is reliable, n, 2, n, 3, n, 4 till n, and x, it's the product of these. Where here actually E, the probability of EI, actually there is a missing conditional here. This should be conditioned on x. All right, so here's another example of use of such models. Let's say that we're trying to look at parsing with weighted finite state automata. If we have some probability of transitions, then if those probabilities of the edges are correlated, then we will be able to use that kind of a model to represent this system. And also robot navigation. If you're looking at trying to find like the best, most reliable path, and you say, well, let's say, I'll give you an example from my Monday. So if you're trying to find an airline path that is most likely to be on time, and you're considering two paths, one through Chicago and the other one through Indianapolis, then you can say, well, if Chicago has some weather issues, then probably Indianapolis will also have some weather issues, with some correlation between them. If the weather is really nice in Chicago, then probably the weather in Indianapolis will be really nice. So here's the problem with this new problem. You could say, well, I showed it to originally to some theory people, and they said, yeah, it should be solvable with some nice techniques. And here's what fails. So in traditional algorithms, in traditional problems, this optimal path that we get from the source to the sink is also uses those subpaths that are optimal. So the path from S to V is the best path, and if the path from V to T is the best path between them, then this is the best path that goes through V. Okay, maybe there is a better path that goes somewhere else, but if V was like an island here that we had to go through, then we could just concatenate the two best paths and get the best path overall. All right? So we could essentially reuse those sub-problems. What happens with the stochastic variant of this problem is that those paths, if I find the optimal path from S to V and the optimal path from V to T, that's not necessarily the optimal path overall. And here's a very simple example, and then I'll give you some intuition for why that fails. So the example is this. So I put some probabilities here. We have one hidden variable that has two values. X is equal to 1 or 2. And this is path 1. This is path 2. And this is path segment 3. And so the probability that, let's say, just to kind of give you, to read this for you, the probability that path 1 is reliable, given that x equals to 1, is 0.9. Right? So when you try to compute, we have this prior over x here. So x is equal to 1 is half, and x equal to 2 is half. So when we try to find the best path from S to V, we compute the marginal over the probability of success of this path, which is just a nice, simple summing out of x from the joint for path 1. And we do the same thing for path 2 and path 3. So let me give you all of this and show you what happened. So this is the best path. According to this summing out, the probability that path 1 is reliable is 0.65. Probability of path 2 reliable is 0.6. So path 1 is better. We have only one path here from V to T. It's path 3. So we have to take this one. Now, if we were going to use Dijkstra's algorithm or something like that, we would choose this path from S to V and then concatenate it with P3. But notice what happens here. The probability of taking path 1 and then path 3 is significantly lower than the one of taking path 2 and then path 3. Now, why did that happen? I mean, there are two intuitions that I can give to you. One is that when you concatenate paths, this is very similar to what people in probabilistic reasoning and machine learning, when they exchange the order of the summation and the product. By exchanging the order of the summation of the product, you assume that these can be essentially concatenated. In this case, that's not true. So, I mean, algebraically, it's not always the case, but sometimes it's a simplifying assumption that we make to get things tractable. Here's another intuition why that doesn't work. The other intuition is that look at what happens when we are trying to see what is the probability of failure of the entire path. We look at the case of x equals to 1 separately and the case equals to, x equal to 2 separately, and then combine them. Here we first combine the solutions for x1, for x1 and x2 for this path, and then look at a separate combination for x1 and x2 on this path. They are separate. They are different options. There are different cases. When here, this path will be really nice when x equals to 1. This path will be really nice when x is equal to 2. This one will be also nice when x equals to 2 and will be really bad when x equals to 1. So overall, this path, the first, taking path 1 and then path 3, will almost always be bad. Either it's bad in the first segment or it's bad in the second segment. Here, at least, for one of the segments, it will be, for one of the cases of x, it will be good. Yeah?
So the natural thing is actually to compute the shortest path given the value of the input variable. And
right.
Then
but
everything works fine.
Right, but what is the value? Okay, so you say, let's compute it for x1 equals to 1.
For every value of the hidden value, the hidden variable, just compute the shortest path.
Right, but then what? We don't. So you take. So let's take that suggestion. For x equals to 1, we will compute the optimal path is this. For x equal to 2, maybe the optimal path is this. Oh, sorry, the optimal path for x equal to 2 is this. For x equal to 1, this one is better. Then the question of how to combine those two paths, it's not clear. And you can say, well, maybe one of them is the best, but you can find examples where both optimal cases for either values of x will be as far as you want from the optimal. None of them will be really close even to the optimal.
Yeah, but given the hidden variable, given the distribution, there is nothing better to do. I mean, eventually you can combine it eventually by amortizing over possible hidden variables, but that's the whole information that there is there. I mean, there is no.
True, but remember, we have a very specific maximization. We have a very specific optimization problem here. We're trying to find the optimal path, the path that maximizes this formula, the sum probability of x times this product. Okay, so what we tried to do is we tried to actually solve this, and what I'm going to show is that there is a way to approximate it.
And you know p of x, you know the probability distribution of x.
I know the prior over x, yeah.
So why not to, given every possible value of x, compute the shortest path and then amortize it with respect to this probability over x.
What does it mean to amortize it? I still need one path at the end. I find the best path for one value of x. I find the best path for another value of x. I still am looking for the best overall path. Gives me the best expected, the best expectation here for success. So I'm trying to send my truck from San Francisco to New York.
You want to do it in a way that's not the full combinatoric solution.
Right. Right. Well, right. I mean, the full combinatorial solution would be just to try all of the paths between San Francisco and New York, right?
But you could use dynamic programming, right? Like they do in MVPs.
Right.
Where you start from the end, go back, propagate values.
So that's exactly what fails here. Dynamic programming doesn't work here. That's exactly the argument, because if you find, what would dynamic programming do for us? It will find the best solution unto Chicago, and then from Chicago, the best path to New York. So that's exactly what fails here. We tried all kinds of tree width, all kinds of dynamic programming. It all failed, and kind of I couldn't believe why. I mean, why would it all fail until you actually showed that it's NP-hard? So okay. So let's examine why. So this gives us an intuition for why it won't work. But now let's see that it is indeed NP-hard. So we cannot reuse solutions. That's the most important kind of intuition that we got from this. So here is a simple reduction, and I see that the colors here are not going to be very favorable to me, but I'll try. So I'll read the first few lines. So this is a reduction from the string template matching. So we have a string template matching is the problem of given, say, several string templates with these are strings of ones and zeros and star, where star is I don't care. And you're trying to find a bit string that matches at least k of the templates. So let's say here in this case above, so for k equal to 2, the answer is yes. So let's see. This one, there's nothing that will match S2 and S3 because 1 and 0 here don't agree. But there is something that will, and there is nothing that will match 2 and 3 because 0 and 1 here don't agree. But there is something that will match both 3 and 1, string template 1 and string template 3. So this bit string, so there is a solution for k equals to 2. There is no solution for k equals to 3. Okay, so that's a standard, one standard NP complete problem. And what we showed is that this is kind of just reducing this problem. We reduce this problem to our shortest path problem, the stochastic shortest path. So what we do here is for every string template, we're going to introduce, so we're going to have one hidden variable value for each template. And we're going to ask, essentially, which template does a string match to? So, so if we're given a string would be 0 if it goes with the upper edge and 1 if it goes on the lower edge. And if you give me a path here in this graph, then that path corresponds to a string. Now I'm going to ask how many of the templates that particular string correspond to. And remember that hidden variable that I have? The hidden variable will have all of the, let's say if I have like n templates, it'll have n values. And I'm going to essentially count what is the probability, what is the highest what is the path that gives me the highest probability in this graph. So if I have a path, for example, that covers k strings, then the probability here will be 1 over, proportional to 1 over, to k over n.
So basically for each subsegment, you're kind of picking out the locally optimal path, and you are over, and assuming that the distribution over x is uniform, you want something that's on average the best that matches all of the locally suboptimal paths.
Right. So this is, remember, this is not an algorithm. This is just a reduction, right? So if you find a path that matches k strings, then its probability will be the k times 1 over n. Because 1 over n is the probability that you fit one bit string kind of, or it's not exactly 1 over n, but this is like the intuition. So if you have, if each one of the strings matches 1 over n of your probability mass, then you're going to try to sum those, those strings, and you're trying to sum those probabilities for matching each one of the strings. Then the problem of finding if you match k strings becomes finding whether you have a path that has a certain probability or surpasses that probability in this graph. All right, so this is just kind of the intuition for why the problem is hard. the previous this string matching problem can be reduced to SAT, and so this is SAT can be reduced to the string matching problem, and the string matching problem can be reduced to this, and so what you get at the end is a problem that is a simple combinatorial problem. Notice, by the way, that it was NP-hard. It is NP-hard in the number of values that we have for the hidden variable. So if we have n strings, it's NP-hard in that n. Okay, I'll write it down because this is an interesting point. So it's NP-hard in number of values of this hidden variable. Okay, so here's an approximation scheme, and what I want to point out to you is that this approximation scheme doesn't really solve this NP hardness. I'll explain in a second. So here's the approximation scheme. We're going to assume for a second that all the probabilities have this property. So the log of the conditional probability of the edge given the hidden variable value is between 1 and some q minus 1 for some q. Okay, so we will have q values for the log probabilities. And what I'm going to do, I'm going to try to create a dynamic program, but it's a dynamic program that will use those discrete values as kind of the setup for our dynamic program. So what we notice first is that the probability that a path is reliable given a certain value for the hidden variable, that's also an integral value here between 0 and n times q minus 1. And as a result of that, we're going to use those integers as our islands in this search. So here's the algorithm essentially. So what we do is this. At each node, we compute the Pareto optimal solutions for a particular set of values here. So here, for each CI, I'll focus on this for a second because this is really the main ingredient of this dynamic program. So if we have d values for the hidden variable, then for value, so we're going to have this kind of product of all of the possible probabilities between 0 and q minus 1 for each one of those hidden variable values. So, for example, I will have this, let's say, 0, 1, 1, 5, 3, 2. And these are the entries in that table. So this, remember, this is the log minus log of the probability of xi given, this is of the edge I, this is edge I given a certain value for x, but now here, instead of the edge, we're going to have the probability of the path, the log probability of the best path that reaches, that comes in with this value. So we're going to essentially, so I said we have here 1, 2, 3, 4, 5, 6. So the domain for xi, for x, is 6, the size of the domain. So for each value, so this is x equals to 1, x equals to 2, x equals to 3, and so forth until x equals to 6. for those 6 values. For each one of those, I'm going to say, what is the path? Give me the best path that comes in with these minus log probabilities. So when x equals to 1, it gives me 0. When x equals to 6, it gives me 2. Okay? So we're going to have this matrix, and for each value here, I'm going to compute the best path, kind of the path, or one of the paths that comes with these minus log probabilities, and that's what I'm going to now use for my dynamic program. Okay, so here's what happens. That's right. It is. The number of things that I will have to evaluate is exponential in D. In D. Not in the number of nodes in the network, but it is exponential in D. So it doesn't really counter this NP hardness.
So in principle, when these fixed, maybe not NP hard.
True?
In principle.
Right.
I mean, you find the approximation scheme for the case where it's not NP hardness.
That's right. That's right. So we were not able to, you immediately see the gap. We were not able to show that it's hard when the domain size is fixed, and we were not able to show an approximation for the NP-hard problem. So here's how the algorithm goes. It's so if we computed those the dynamic program until a certain node, we are then going to use those paths. We can then use those paths to compute the best, or kind of those paths with those probabilities to V. Now the important thing is, here we're going to actually use all of the paths that came in, all of those that we cached in our dynamic program. Okay, so remember we cached here, what was the number? Some polynomial in n to the power of d. All right. So this is a lot of combinatorics for the machine learning people in the crowd, but it's an interesting problem that really doesn't yield to the standard techniques that people use in machine learning.
Can you say something on how bad regular dynamic programming is? Is it arbitrarily bad?
Yeah, I can show you very simple examples where it fails. Where it fails badly. I mean, as far as you want from the optimal.
Do you have any guarantee on the performance of this?
Time?
No.
The approximation. The approximation. So the approximation is really here. The approximation that you get is essentially this. In time that is proportional to 1 over epsilon, you get kind of, if opt is the reliability of the optimal solution. So remember, this is probability of that the path is reliable. You get a path that is more reliable than opt to the power of 1 plus epsilon. So epsilon is really, so I assume that all of my probabilities are in those discrete buckets, right? And so you will use that epsilon to round them in some way. Okay?
Better or worse than 1 minus epsilon times opt? It's likely, because usually this is how...
So the opt is less than 1. Remember?
Yeah, so it's always better.
Oh, I see. 1 minus epsilon.
In approximations algorithm, you write
1 minus epsilon times opt.
opt and not to the power of 1 plus epsilon.
Right.
It's the same here, or it's actually it's
I don't. I have to say I don't know. I think kind of my intuition is that this is worse than 1 minus epsilon times opt. But this is, we can sit down afterwards and just write down. It's very simple. Yeah.
This is probably worse.
It's worse.
Yeah. Because if opt is very small, yeah, very low. trouble.
Right.
So it intrigues me that the way you've laid out the problem might be interesting to some of our probability theorists, because we have nice results from graph theory on reachability based on and things like critical values and phase transitions and so on. Imagine defining a problem where you have some dependency with some named distributions and seeing if you can actually prove something about critical values and critical dependencies and so on. It's just kind of an interesting playground, it seems like, for new sets of problems. Not necessarily solving the reachability directly, but looking at for particular values for critical thresholds that might be met. This is a kind of, I know it sounds like a very tough area to work in, but it's interesting. Have you thought about that at all? Looking at some of the kind of the results in random graph theory and reachability parameters, and thinking, oh, what kind of class of problems might I define for that community with dependence model?
The thing is, there are different dependence models for different applications. The answer to your question is no. I haven't gone in that direction, but there are really different dependence models that one would like to have, like those dependencies between different roads that I'm going to use through Chicago, or different dependencies of just many different random variables that are hidden and affect the system.
Yes, we'll have to take it offline, but we have some interesting routing problems that might,
All right.
where depending on which route, you have traffic conditions that are changing, and depending on your forecasts of your weights over time, you have different worlds reached at each segment when you finally get there. And depending on, so you have some interesting intrinsic dependencies that will happen given where you go that might map to this problem.
One interesting kind of just a piece of gossip about this. People ask me why we didn't. We presented this in UAI of last year, and people asked me why we didn't submit it to a theory conference. And my answer was that people in theory are interested in this, but they are more interested. This is not a fundamental problem, whereas also the AI community is more interested in those dependency structures between random variables. The UAI community or the AI community is less, is not as good as theory and combinatorial algorithms, but it is a set of problems that are of real use.
But even in statistical physics, people are having a hard enough time with independence right now. So.
Right.
There's another layer of complexity.
All right. So let me just summarize this part, and I'm going to quickly switch to the second part, and again, try not to get you too tired. By the way, you can still ask me questions. I love any questions that you have. I just want to not get you too tired. So here it is. So just what we've shown so far is that there is an interesting different model for reachability. One can use different uncertainty models, and it's a very interesting problem where a lot of different techniques come into play. It is NP-complete, but we still have a very important gap here between the kind of this hardness that depends on the size of a domain and the p-test that we had that is exponential in the size of that domain. All right. So the second part of the talk, this is slightly completely different and something that is more in line with machine learning theory, is a different problem where we're looking at inverse reinforcement learning and trying to add knowledge to it and kind of probabilistic prior to on top of that learning problem. So just to kind of explain to you what is inverse reinforcement learning, here is an example. We have this game, and this is just an adventure game where a player moves around in a dungeon, collects treasures, and avoids monsters, and so forth. And what we see is that if I look at somebody who plays that game, I can learn a little bit about how the person solves the game, and the interesting problem from the perspective of AI is how to really learn there, and what are you learning in the result. So what people have done, what people typically do is they try to either pose the problem as a Markov decision process. I'm going to describe that to you in a bit. But kind of more recently, people have tried to use approaches to learn those models, the Markov decision processes, and that's what we're going to do here. So what we're going to do is we're just going to describe a Bayesian model for inverse reinforcement learning, or learning the model of the expert's choice of actions. And we're going to use that model to then find the most efficient, or the most rewarding set of decisions in that domain. So our intuition here is that we would like, in the learning process, to incorporate some domain knowledge, something that will help us learn a little better from that teacher or expert, or from what we observe. So here's the model that we're going to use. It's a very standard model in machine learning. There's a Markov decision process where we have a set of states, actions, transitions, and a discount factor. We're looking, typically, we assume that the expert will use a certain policy that maximizes his future rewards, or something, kind of the expected future reward is really the sum of reward from the current state and the next state and the state after that, and so forth, with some discount. So the farther we are in the future, the more discount we will apply. This gamma here is less than 1. Yeah?
So why don't you have the reward as a part of the model definition?
Right. So our problem here today would be to actually learn the reward structure.
So there are rewards, you just don't know them.
Right. We know that the expert uses a reward function. We're going to assume something about that reward function, and we're going to try to use those assumptions to learn a reward function that is more likely to succeed, or more likely to be the correct one for the expert. Mm-hmm.
So usually reward means something that is given from the environment in reinforcement learning. So it's not it's okay to assume that you don't know the reward, but when you say that you want to learn a reward that is good for the expert, you're saying that the reward is not something that is directly observable,
right.
But it's something that you can play with.
Right. Right. So, for example, the motivation, we did not come up with the inverse reinforcement learning problem. That was originally posed by Andrew Ng and Stuart Russell like 10 years ago. And their motivation was, we want to learn how to, for example, in the case of Andrew's motivation was, I want to learn a model that will allow me to control, say, a helicopter, or control some unmanned aircraft vehicle. I don't get those rewards. I don't know. I can see only what that expert is doing. I don't know what is the reward structure of that expert. I can pose some rewards, but I really would like to know what are the rewards that this person is having, so that I can use those rewards in my solution of the problem. So there are those cases, and in fact, what people sometimes do in reinforcement learning, they assume some reward structure of some sort, either by guessing or by kind of trying to smooth a certain threshold reward function. So we're going to try to, instead of doing that, what we're trying to do with this work is try to learn the reward of that expert. We already see the experts doing its actions. We don't know what the reward is. Let's try to learn that reward.
Strange, because you want to maximize something. So what are you maximizing? If you get to choose the reward, then I choose that the reward would always be 1 million, and then I'm maximizing, right?
Right. No, right. So there will be 2 optimization problems that we're going to solve here. One will be to have the kind of minimum distance from the real reward of the expert, and the other one would be to maximize the expected rewards. We don't know what those rewards are, but we would like to maximize the expectation of our future rewards. All right, so I'm going to give a little more details, and maybe we can explain that a little more. So I'm going to use this Q function that is typically used in reinforcement learning. It essentially says essentially represents for a policy pi. Policy is the way that you choose your actions. For a policy pi, what is the expected reward for a certain state and a certain action that you're going to perform in that state? Now, we're going to modify this Q function and add this extra variable r for the reward. This is a reward function that will be part of our Q function representation. All right? Remember, what we're going to try to do is we're going to learn that r, but if you give me that r, here is the evaluation of that Q function. All right. So here's our assumptions. So we're trying to, and this is, by the way, these are assumptions that this is our assumption that, this is an assumption that was actually made before this work. We're going to relax those assumptions in this presentation. One is that X tries to maximize the accumulated expected reward, and the second thing is that X executes stationary policy, and that stationary policy was learned by a reinforcement learning algorithm. This is the assumption about the expert. Previous assumptions were also, by the way, that the expert is doing something that is optimal. And we're going to drop that here. We're going to allow the expert to be suboptimal, and also we're going to have some prior over what the rewards could be. I'm going to give some examples in a couple of slides. So let's say that we are given this prior over rewards, and now I'm going to try to just analyze what one can do with that prior. Remember, so I'm going to just write it down here for example. So the reward of being in a state where you have the gold, or you get the gold, let's say that is, say, the number 10. Just to kind of, if you've never seen anything like this, then it will be a little bit, just to give you some intuition. And the reward for no gold is, say, -1. Sorry, this is a little low here. I'll erase this. This is just an example. So the reward function is really, no gold is -1. And the reward function is just it's kind of just a function from, could be a state times action to some real number, or it can be just a function from states to rewards to a real number. Doesn't matter. Most of the time you can translate from one model to the other. So what we're doing here is, I said, we have a prior over those rewards. We don't know what the rewards are, but we have a probability distribution that governs that reward function. And what we're going to do is we say, well, we're going to observe some things, those observations. These are the actions that the expert have done in those states. So in state 1, he did action 1. State 2, it did action 2, and so forth. We're going to assume that given the reward function, all of those actions are independent. What does that mean? So if somebody already gave that thing to me, then the probability that the expert will choose action 1 given S1 will be independent of the probability that the agent will choose action 2 in state 2. Okay, it's a very simplifying assumption. In some ways, it allows you to introduce many different reward structures, many different experts here but it doesn't matter, just assume this. What it allows us to break this probability into is just a product of the probabilities. So all of my observations, all of the things that I observed about that the agent has done, that probability is really the product of the separate actions that the agent did. So here's what this boils down to. If we have a probability that so for every state and every action, that probability given the reward it can be represented with this simple exponential representation with some normalizing factor times e to the alpha x times this q function that I mentioned here before. Now remember, we don't know r, but if we were given r, we would be able to compute this q function. What is this alpha here? This is some measure of the expertness of the guy who does the demo for us. So we allow the person to be wrong. We just kind of measure the number of times that he will be wrong with this alpha. Okay, so what this does, I said the probability that Si and that at state I we choose action I given R, that's independent of the choice of other actions in other states, and so the probability that we will get all of those observations is just the sum of those q values times alpha x. So it really boils down to a nice formula, and what we can do with that is we can now invert that formula the other way around using Bayes' theorem, and now we can compute the probability of R given the observations. So that probability is just some normalization factor times this, and now we can include the prior here. So far I just did very simple manipulation of those formulas. Now the real question is, okay, so what do we get from this, and how do we get the optimal reward? There are two optimization criterions that we would like to satisfy in different situations. One of them is we try to learn the reward, so we can use a different loss function, either L1, L2, or whatnot, whatever is most useful in your particular case. This is one problem that we would like to solve. The other problem that we would like to solve in other cases is to find the best the best policy, the policy that minimizes the expected loss according to whatever loss function we use here. This is you could usually kind of like use whatever norm you would like here in this loss for the policy given this reward. Okay, so these are the two minimization. This is the two optimization problems that we would like to solve. And the ways that we kind of, so far we just posed the model, said what is the optimization criterion, is, and now we would like to solve this. And there are two, there's essentially one main solution method and two different cases. The main solution that we're going to use is an MCMC sampling technique where we essentially evaluate Q star and then use that to decide which reward function to go to next. So what we could do is we can change that policy. Let's say if what we're looking for is the optimal policy, we can change that policy to keep track of kind of to not compute this Q star. We're going to be able to cache some of the values for it and use the Q star just by looking at the previous values for it. Use the previous policy for that we used with the previous R. Now we're going to change R a little bit, and so once we change R a little bit, not all of the Q values are going to change, and so we can use the previous computation for the policy, the chosen policy, to now estimate the new Q value. Yeah.
I don't understand what you mean by keep track of the optimal policy.
All right. So let's say for a particular reward function, we now compute the optimal policy.
So you start with some reward function that you guess. Okay.
That's right. Now we're going to change. We're going to use MCMC to perturb this reward function a little bit. We're going to now choose a different reward function, evaluate the probability that that is the reward function in our model using the previous model that I presented. We can now compute. I cannot optimize the reward function given that form that I showed, but I can evaluate for every reward function. I can evaluate that probability given the observations that I had. So I'm going to evaluate that new reward function that I'm now proposing, and with some probability I will change the reward to that structure. Now I have a problem that in order to compute every time that I'm trying this MCMC step, I need to evaluate this Q value in order for me to remember that Q was a participant in that in the computation of the probability of R. I have this probability of R given the observations of the expert's actions, and that included something. There was an exponential model with some sum of Q values. So I need to use this in order to evaluate this. Now to use this, every time that I'm going to even try to make a step in my MCMC, I'm going to spend a lot of time computing that Q function. And so to compute, that Q function, I will, it's important to essentially try to do something smarter than just brute force computation. Yeah.
Isn't there a policy mismatch between the policy that you're learning down there and the policy that was being followed when you collected your initial observations? Is that one of the problems?
So say it again?
So you're trying to estimate the reward function given an observation sequence, and presumably the Q values are defined in terms of a policy, generally, aren't they? And
Right.
so wouldn't your actor or your tutor have been following a different policy, perhaps, or a suboptimal one? Or
Right. No. So you're right. So the tutor may have followed his own policy, but I assume that. So I don't know what is the optimal policy, and it might not be the tutor's optimal policy. But I'm going to try to estimate the reward function, and in order to estimate the reward function, so I'm going to use that estimate of the reward function later in choosing my optimal policy. I don't know if his policy is the optimal one, but I'm going to try to choose to estimate R in some, for the two different optimization problems. I'm going to do it. I'm going to do a different kind of estimate here. But here, if I'm looking for the most likely R, I'm going to need to use and change the policy because the Q value really will depend on the policy, and I don't know what is the policy. See, the Q value, I don't know what the policy of the expert is.
So you're not necessarily.
I just see.
So there's two policy estimation problems here. One is kind of nested in the R estimation problem, and then there's another policy estimation problem that'll happen later.
Well, no. So it won't happen later. I'm not trying to estimate what is the policy of the expert. I just see the actions that the expert did. Okay? I'm just going to try to estimate my optimal policy given my prior, because I don't know what the rewards are. All right. So what happens is we compute Q, and then we use that to compute the probability of the R that we're testing right now. And we're going to use that in a hill climbing kind of, it's not really hill climbing, it's an MCMC step that will, to get to an estimate of the most likely R. So interesting things about this procedure. So I kind of described this procedure really in 2 words, but in this procedure, what happens with MCMC is that you create samples you have many steps of this changing of the reward function, and after say 1,000 steps, I reach some reward function, and I take that as a sample. This is one sample, and now I'm going to start my MCMC again, or I'm going to run this chain again and again. I'm going to run it many times until I generate samples of my reward function. Using those samples, I can then estimate what is the most likely reward function. I can estimate also what is the expected, let's say, the policy with the maximum expected sum of future rewards. So I can use the samples for whatever I want, but in that MCMC step, the basic step really generates those samples of rewards. So there are two interesting things that that I want to say about this sampling method. So one of them is that when we have a uniform prior over the rewards, turns out that this Markov chain rapidly converges, rapidly mixes. So you don't need to make too many steps in order for you to create those samples for your estimation problem. So typically, you don't know how fast your Markov chain will mix, and so you have to run it and just hope that it will be fine. This is not our result. So I mean, it is our result, but it really derived from somebody else's result on sampling in convex regions that are uniformly distributed. So uniform distributions over convex regions. And so here, this is the citation that we used. And the second thing is that even in those cases where, so this is nice just because it guarantees for us some rapid convergence of the algorithm. The second thing that I want to show is that really this in experiments, even without the uniform prior, this thing converged relatively well, relatively fast, and to solutions that are better than just the standard IRL without such priors. So here I compared two versions of Bayesian IRL, one with Q learning and the other one with K greedy, and so what you see here is so the top. These two lines here are from these are the expected reward loss. Kind of this is when we were trying to just learn rewards. These are more. This is the standard IRL, and these are the two new Bayesian IRLs. So just to kind of explain to you, the lower the curve, the better it is, because what we're looking for is something that has a zero reward loss. So, what you would.
Is n the number of iterations?
No, sorry. N is the I think is the size of a domain that we experimented with. We tried it on different. Yeah, the number of states. And here's I want to show you. This is the kind of the policy loss, meaning. Sorry. Just a second. And this is the same curves, but now the expected, kind of finding the policy that maximizes the expected sum of future rewards. Again, you don't know what the reward is, but given the expected reward with these priors, this is what we get.
So you said that you assume that the expert is not optimal, right? You said that earlier. That's the alpha in
Right.
situations. And so what you're showing here is the difference from the policy of the expert, no matter how non-expert he is, or the optimal rewards, the optimal policy?
This is the difference from the optimal policy. I think that we used we didn't try it with different alphas. We tried it with a fixed one. I think it was like a relatively high one. But I know we didn't change the alpha. So, but this is the difference from the optimal policy in that particular domain. We tried it on 2 different domains. I think these graphs are of the adventure game example. I want to show you one more graph here in this adventure game. Here's just one more example of a prior. We used like an Ising model like prior, where when you have the when you have the treasure, then you will have higher rewards, and so you assume. So this is something that we can assume as a prior over the reward, and then we correlate states that are adjacent. So if 2 states are adjacent, they will have a higher reward supposedly. And so this kind of prior, we then applied it to this adventure game, and you can see that with this nice prior, you could get better reward loss compared to our expert that is trying to play the game and knows what it does when it plays that game. We used over there we used, I think, a shaped reward function. And so here, just kind of a very simple kind of measure of how the reward loss was a little better. All right. So I said I'm going to try to tie it together. I gave you about an hour talk. So let me just try to summarize what we've shown here in the second part of the talk. We tried to generalize this inverse reinforcement learning problem, introduce some different priors. The motivation was to both allow us to learn reward functions when we have some knowledge about the domain. And secondly, if you look at the problem of inverse reinforcement learning, you usually get relatively little data, and you have a convex domain that has many possible solutions. To choose one of those solutions over another is a matter of heuristic, unless you have some prior knowledge over R, and that's what we tried to solve here. The computational problems here are still pretty big, but for those small domains that we experimented with, it was manageable. So that's it. If you have any more questions, I'm happy to answer them. Thank you.
Great, thanks very much. And you have papers on these 2 topics?
Right. So we have papers on this. The first one is in UAI. It's Uncertainty in AI 07, and the other one was in IJCAI of last year also. So this is number 1, this is number 2.
Just a remark, I think, I'm not sure that even for the first problem, even if you have only 2 options, it's already incomplete.
You think?
I mean, I have some kind of proof, but I can talk with you offline.
Love that. We'll love that. That would be interesting. All right. Thank you very much, then.
Okay.
Thanks.